the three different configurations of transistor. This we have touched upon actually before the CAT exam itself, that we usually have three specific configuration of BJT by which it can be used in a circuit. The first one being the common base mode, then we have a common emitter mode, and the other one is a common collector mode. And the respective circuits are also provided in this particular slide. As you can observe very clearly that when we are looking at the common base connection, the base is grounded. Okay, so the base is grounded over here. Those who have uh, already done it, already done the experiment, you can understand, you can relate the circuits. We have done the common emitter actually in lab, but this is basically the circuit that we are looking at. The base, the ground is connected, so the base is here, the emitter is here, and the collector is here. And remember, I just want to recollect once again that this is an NPN transistor. Why? Because the arrow in the emitter is actually going upward. It's going outside, like it is going away the screen. Okay, so that's why it is an NPN transistor as well. As I said, PNP could have been also used, but we will not use that. Any one is fine, but NPN transistor is better because in electron is what we are more familiar with. Holes is just an opposite to electrons. It doesn't exist as such. So we are more into the electron domain. So that's why we usually consider the NPN transistor for most of our operations and understanding. So this is my common base configuration. This is my common emitter configuration, where the emitter is grounded, and this one is a common collector configuration. Now each of them has their own advantages. Each one of them has their own applications for that matter. Primarily for the one of the most important application of transistor happens to be the amplification. Remember this, okay? And switching action as well. Amplification will come later in this fourth module. We will discuss about the amplification there. But ideally, these are the two best possible application of a transistor, in which the CE configuration, which is this one, the common emitter configuration, this is ideally suited for the amplification purpose. For all the amplifiers, in audio amplifiers, the one that we usually use, or signal amplifiers, or any devices, electronic devices that we come across, for all the cases, common emitter configuration is the most generic usage. Okay, but whereas with respect to the switching action also, you will find that there are different modes in which a transistor will be used. All right, and based on that we can apply the transistors. For example, the common collector right over here, it's very rarely used, but it's the usability is for impedance matching. Like if you have two circuits, two separate circuits, and you want to match whether the load is matching or not. So all those cases, the common collector configuration is a very commonly used application. High frequency application will have common base process, but actually common base and common collector, these are not very we are not very fond of it as such, because common emitter is mostly used for our lab, for our discussion, and for most of the analysis purpose as well. So in that aspect, in fact, before the lab, before the CAT, we have also discussed that what are the parameters that are important with respect to these modes. In that, one of the first parameter that came across was called as the alpha, or the current gain. Now, if you observe the common base configuration, which is this one, okay, you can definitely observe that the IE happens to be the input current, because this is my input signal, whereas the IC is the output current, which is the output signal, because the output is over here. So if you take the ratio of IC by IE, which was here, it was considered to be something called as alpha equal to IC by IE. And this parameter is important because each and every transistor which we are going to use will have these specifications. So every material, the way it has been built, will eventually influence the nature of amplification or nature of switching and the nature of application for that. So that we have already discussed. So even the other part, which is the common emitter configuration, which is this one, here also you can see the input signal. Just remember this very carefully, the input and output, because this input and output will play a very significant role while we discuss about the characteristics of these configurations. All right. So CB will have an input output characteristics. CE will also have its input output characteristics, as well as CC will also have its input output characteristics. Whereas now if we come to CE configuration, the input signal, if you observe, this is my IB, so the base current is 1, whereas the output signal is basically IC. And based on that, if you remember, we had already discussed that IC by IB or output that of input. Okay, this is what we are looking at as a current gain. All right, and also if you remember, we are also derived that how this alpha and beta are related amongst each other, and we have also observed that the value of beta will lie between somewhere around 20 to 300. Typically, the value is around 100, whereas for the alpha, the value is the value is close to 1 mostly. Okay, it will come to somewhere over here in this example, it's mentioned as 0.719. So it will be nearing about 1. If it is near to 1, it is better for the system, like that. All right. So that's how the parameters of current gains were calculated. Similarly, for common collector, we got another one which is called as a gamma, which was again the same way, IE being the output and IB as the input. The configuration is different. You can observe that the collector is now grounded. This you be very careful while drawing the circuits. Later on, if you are asked to find out, please mention or please understand the application of it. In this case, the collector is grounded. You can see over here, it's mentioned collector terminal is grounded and make on. Okay, so this is where we actually ended. I just wanted to recap again because this happens to be the base at which we start our discussion for today. Now, based on these three configurations, as I said already, the first configuration, the CB configuration, as we know, we need to understand what its input and output characteristics. Now, why it is important? Because based on the input and the output characteristics, we will try to specify that particular transistor. That what is their operating point, what is the nature of its cutoff, what is the particular voltage after which it might create some problem or it might burn out, like that. So these specifications can only be measured if I get a hold of a characteristic. Just like we had diode characteristics, similarly we can have transistor characteristics. Now, if you observe here closely, that in this particular most of the things are mentioned over here, and fortunately for one of the half of the batch, the L5 L6 lab batch, you already have done this with respect to CE configuration, and we have observed a very similar kind of graph in there as well. So in this case, although there was some different in logic as well, we'll come to that, but let's see one by one what are these input characteristics. So if you observe here that in case of CV configuration, which is over here, the input that you are looking at is the VBE, which is the base to emitter voltage. You can see over here. Okay, I'm marking it. All right. And whereas the output is nothing but the VCB or the collector to base terminal. Now, as I already had mentioned in lab, but now I think it will be better. You can see here, this is a power supply source. So ideally in some books, this is called as VDD. Like it is a power supply, a hardware module, and ideally the difference, the potential difference that is across this terminal, if you observe the arrow that I mentioned, this is usually called as VBE. This is called as VBE or the base to emitter voltage terminal. But ideally this cannot be a voltage supply, it is a kind of voltage drop. Okay, and most of the time this is equivalent to VBB. That's why in general cases we might assume this power supply as the VBE itself. Okay, I'm repeating it once again what I mentioned over here. You can see everywhere I have mentioned VBE is increased like that. But VBE is basically a base to emitter voltage, as I mentioned over here. Now the supply voltage, this is not a supply voltage, it's basically a drop that is associated when we apply a voltage, a hardware battery supply, a power supply, as in terms of VB. Alright, so this is basically the nomenclature should have been used, but as in most of the cases, this VBB is equivalent to VBE. That's why we colloquially will mention it together. Right. So this is about the VBE part. So now what happens that the output, the input characteristics. So input characteristics, what does that mean? Remember, in case of CV configuration, my input was IE. So this is my input. Okay, so if the characteristic is with respect to IE, then we are looking at input characteristics. That how the input of IE, or what is the maximum limit of IE that can be provided for CV configuration, given that we are increasing the VBE in the x-axis. Right? So how do I do? This shows how IE varies with VBE. Alright. Remember, the y-axis is the current axis. So it's basically giving us kind of a scaling of how the current is behaving or how the current is changing with respect to the input voltage. Now, for that to happen, the first thing where we start off, this actually we can be proved in lab only, but for those who have already done it, remember that we have started off with the voltage should be 0. So same way, VCB is considered to be 0. Connected to base terminal, the voltage is equal to 0. Okay, and VBE is increased to get IE. So you can see here the first curve over here, VCB is equal to 0. So we are getting a curve which looks similar to a diode characteristic curve after a particular voltage, for example, about this point, okay, or somewhere close to it. You can observe that there is sudden rise in IE that is expected. Okay, so it's can you see the second point? It shows a very similar graph to a PN junction diode, and also you can observe that there is a small little current, a small little voltage somewhere over here, okay, which is sometimes called as a knee voltage. After which the IE current starts to increase. Okay, see the term knee voltage also is very similar. How about a knee is like this, right? So after a particular point, we are actually having a knee joint like this. So same way, the knee voltage is also looking at like that only. After a certain point, the graph is increasing. Alright, so that is a knee voltage. Usually, this knee voltage will vary based on the diode, whether it's a silicon based SI like silicon based component or a germanium based component, like that it will vary. But the important factor is, now if you observe that as we go on increasing VCB, see 8 volt, 18 volt, if I go on increasing the VCB, what is VCB? VCB is this side. So listen to this very carefully, all right? When VCB is varied to a constant value, the width of the base region will decrease. I'll explain it everything, okay? Just for the time being, you understand this. Thus, it results into lesser combination of charge carrier and hence more forward current or IE, and that is called as early effect. Okay, or sometimes we call it the base width modulation. Okay, let us see what is this. It's a beautiful phenomenon that actually happens in a BJT. So let me just explain you through the journal. All right. So let me. So this is a very important portion or phenomenon, I would say. Give me just 1 minute to. Yeah. So this is what we are discussing is called as early effect. Okay, this is called early effect, or we call it the base width modulation. Please make a note of this. This is not there in the PPT, and the explanation also at times confuse people. So be attentive. So what happens that if I consider, okay, we have a PN junction. Suppose we start from the PN junction, and because that will recap on our understanding a little bit. If you observe that in a PN junction, if I do a reverse biasing, so how do I do a reverse biasing for a PN junction? The N side, as we know, it should be positive supply, whereas P side will have a negative supply. Because if that happens, then what is happening? This N, or the electrons which are present in so electrons are the majority carrier in N side, and holes are the majority carrier in the P side. Remember this. This is coming from the diode. Everyone agrees? Everyone agrees to this? We are all at the same page, right? Guys, please respond.
once can you repeat? Yes, sir.
We are discussing the early effect or a base with modulation. This is a new term associated with transistor. I'm trying to explain it from the point of view of a diode. Then I'll come back to transistor. So what I'm discussing here, that this is a PN junction diode, and if I want to make it reverse biased, suppose this is reverse biased, and the way we are reverse biasing is that this majority of the electrons which are there in the N side will be attracted towards the positive terminal, and so electrons are attracted like this, whereas the holes will be attracted towards the negative terminal because holes are positive and electrons are negative. So this is how the reverse biasing works. But on the contrary, we have also observed that due to this process, due to this movement of holes and electrons, there will be a portion across the junction primarily which will have the immobile electrons in the p zone and immobile holes in the n zone. And if you remember, we had also discussed that this has already been taught to you. If you remember that this particular region was called as the depletion region, or we call it the charge free region, because these are immobile charges. Okay, they are not the, it is only because the electrons and the holes have dispersed into two directions. That's why they have the immobile charge got exposed. So these are the depletion region. So whenever there is a PN junction or an NP junction, whatever it is, but if it is a reverse bias that is happening, definitely there will be an option where the depletion region will be generated. Now come back to a PNP transistor. Now you have a transistor like this. Suppose I take the example of PNP. It will apply same with NPN as well. So let us have this as PNP, because like this. Now what we are doing is that for a PNP, most of the time what we are trying to do is that the P side, that is so this is my emitter, this is my base, and this is my collector. All right. Okay, now we are getting this as forward bias. So P type is there. So if I need to make it forward bias, okay. So what I am going to do, I'll make this arrangement, because this is my plus, this is my minus. So plus will offer resistance to this plus over here, majority carriers. Hence the electrons or the holes will move towards the right hand side. I'm just drawing it, although it is not needed, but this will be the first part. On the other hand, we are making this as reverse bias. So how can I make reverse bias? I can make this as reverse bias like this. So this is my forward bias and this is my reverse bias. Why I'm doing this? So I'm repeating it once again. We are discussing early effect or we call as a base width modulation and how it works. So here we are observing that in PNP transistor or a BJT, if you observe, if you cross sectionally, if you observe that this is basically a PN diode and this is also an NP diode. The same question that I asked in CAT. All right. So this is the configuration. Now, based on this configuration, what we are assuming that the emitter based junction is forward biased and the this part, the collector based junction, is reverse biased. Now you can observe that the first part, if I consider this part A, if part 1 if I consider, so 1 there is no problem. Why there is no problem? Because this is a forward bias, so the depletion layer will not be that effective. The depletion layer is not effective because depletion layer will only happen if there is a reverse bias. But this side is forward bias, so there is no problem of depletion layer in this region. Correct? Am I correct till this point? Towards and also you assume that also we have discussed that the two things, one is base region is very small, or I would say slim, that area, and also it is lightly doped. This two assumption is already there for any transistor action. All right, so this is one of the action. So what we are observing that this junction at 1 will not be having that much of a problem, so it is okay. But if you observe the junction 2 over here, so this part is reverse bias. Just I'll put two diagrams together so that you can understand this reverse bias. Similarly, what will happen near to this junction, there will be a depletion layer which will be formed like this. All right, so this will be some depletion layer that will be formed, because this is also an NP diode, right? And what will happen, so if I write here that due to this reverse bias voltage, the depletion layer will be generated. Depletion layer will be formed, okay? But what will happen, that this reverse bias is nothing but VB or VCB, the collector to base terminal. So what we are observing, that as we go on increasing this collector to base, this RB is nothing but VCB as per our terminology, and this forward bias is nothing but VBE. So as we go on increasing VCB, what will eventually happen? This depletion layer will go on extending it further. So I'll remove this part, okay, and I will now say that this whole portion of the layer is the depletion layer. Because why? Because I'm increasing the reverse biasing. As we go on increasing the reverse biasing, this depletion layer is increasing. Am I okay with this? Everyone is okay with this? Reverse bias causes depletion region, as we have already stated over here. Now, as we go on increasing the reverse biasing, more and more depletion layer will happen. It will form more and more depletion layer. Is it fine, everyone? If that happens, can you observe very clearly that as it goes like this, now the effective, if I write it here, the effective band, effective base width is now only this much, which was originally this much. See this, originally it was like this, the red color part, but now effectively the small segment which is present over here, I'm shading it for our purpose, is now like this. So what does that mean? That is, the base width has been modulated or shrinked based on the reverse bias voltage which has been applied, right? If you go back to previous few slides, I told you that the base region is so this particular process, first of all, let me finish off on this. So this process of increasing reverse biasing voltage affecting the base width is ideally called as the early effect. This is a very important and significant phenomena that happens in a BJT. All right. So when you go on increasing the reverse biasing voltage, your depletion layer will increase, and eventually it will reduce the base width. So this is called as the early effect. Now, what is the effect of early effect? Let me write that. Effect of early effect. Any doubt till this point? Please let me know. Effect of early effect. First of the effect is, I can observe that the recombination of electron and holes are reduced. Why? Because the base width itself is small. If the base width is small, and we have already assumed that the base is lightly doped, so definitely the recombination that was around 2 to 2.5%, 2.25% in a transistor, that is significantly reduced. And what does, if the reduction in recombination happens, what will happen? Can anyone tell me? If the recombination of electron holes are reduced in the base region, what will happen? Is there anyone who is eager to answer for this from the concept that we have learned so far?
So can you repeat the question?
The question is, due to early effect, we are observing that the depletion layer is increasing, and it is like sweeping the base width to a certain extent. My remark is that due to this early effect, the recombination of the holes over here at the P region and the electrons which were there in this N region reduces because the base width is small. As the base width is small, definitely N is slightly doped, so it will have very less amount of electrons compared to the holes if it is a PNP transistor. So what my conclusion is that the recombination of electrons and holes are significantly reduced. Now my question is there any specific advantage to this if the recombination of electron and holes are reduced in the base region? Can you tell me? Just think of it a little bit. What was the base used for? Base was just a combination. It's a sandwich between emitter and collector. Now you are reducing the base. You are reducing the base. Reducing the base. What will happen? The emitter and the collector are coming closer. Not closer, but basically there is no boundary in between. There is the sandwich is going less thin. Okay, it is less thin. So it's basically what I mean is that the electrons which or the current, or suppose whatever the emitter was emitting from this side, that will go more towards the collector side without getting recombined and getting lost. That's the significance of that. So as the recombination of electrons and holes are less in the base region, the more and more collector current will be received. So you can observe that eventually will help in a very important equation which we already know as IC equals to, or alpha equal to IC. Because this IE will not change much because because you can see that the connection itself, this part is untouched till point 1, okay, junction 1, it's untouched, nothing has happened. It is just generating the same way. But during this, because of this junction, because of this depletion layer, towards the collector side, more current is flowing. Hence, we can observe that alpha is actually increasing. Now, if alpha increases, definitely the beta will also increase. Although the beta is a parameter for the CE configuration, but you can observe that basically you are increasing the beta as well. And as I said, beta is a very important factor with respect to the amplification as well. All right, so that is how it's like cascading. One is making an effort to another. All right, so this is another second effect. And the third effect, we call it as a very common term, and that is called as punch through. Okay, this is a term used, punch through voltage. That is when we are increasing the VCB to an extremely high value. When we are increasing VCB, I'll write it down over here. When VCB is increasingly high, so what will eventually happen? The depletion layer will be so much that the base width will be completely zero. So the base width will almost be equal to 0. As they are 0, so basically a 3-terminal device will act as if a 2-terminal device. And that is what we called as, and there will be definitely a voltage breakdown that will take place. And that particular phenomena is called as the punch through voltage. All this is why just to affect this one word, early effect. So now if you observe, when VCB is varied, if I go back, when VCB is varied to a constant value, the base region will decrease. Now I hope all of you understand why base region is decreasing. Thus, the result is lesser combination of charge carrier or recombination, and hence more current of IC as well as IE, or more forward current, and early effect is what makes this thing happen.
Sir?
Understood? Yeah, please.
In your previous PPT, what is
You're saying here?
yeah. Not
Okay.
in your handwritten.
This one only. Okay.
Yeah.
I is the emitter current.
Okay.
This is the emitter current. Emitter current is generated because this part, if you observe the first part, this is forward biased. So the forward bias will initiate the IE current. What I want to say is that till this portion, it is untouched. It is just acting like a normal PN junction diode. But whatever magic is happening is this second half, this part,
Yeah.
where the depletion layer is making this all kind of changes. All right. So
What is alpha and beta over there?
Alpha beta we have already discussed. Oh god. Alpha beta we have just now discussed over here. Alpha is the current gain of the transistor in a common base configuration. It is a ratio of IC by IE. IC is the
Yep.
output current, IE is the input current. This is about the input characteristics. Now, so you can observe that the more now I think all of you must be aware, like as we are increasing the collector to base terminal voltage, the current is increasing, and why it is increasing. Okay, so this is the effect and the nature of it. Similarly, as we have discussed already, the Rin or the input resistance can be very easily calculated as the ratio of VEB to that of IE. So this is VEB. So you can see, suppose I take this point around this and I take somewhere here. So the difference over here will be the del VEB, and for this particular value, if I go like this, I have already shown you in lab also. So this will be my delta IE. So you take the ratio of delta VBE to that of VE, you will get the value of Rin for this particular voltage value of C. Similarly, for different voltages, you will get different values. Alright, let me just finish off the output characteristics at once and then we'll finish it off. So this is basically the output characteristics of CP configuration. Same explanation, similar kind of trend that we can expect. So you can see that it shows the output IC, okay, IC is over here versus VCB. So VCB is over here. Okay, so output current is IC. Remember the circuit connection, it is like this, and keeping IE as constant. So the input, the emitter current is kept constant. You can see the variation, it starts from 0, 1, 2, 3, 4, 5, 6, like that it will go on. Okay, so based on this different IE current, the values are changing, or the graphs are supposed to be like this. This can also be done in lab, which we might test at some time later as well. Two important things over here to understand. One is that you can see IE equal to 0, this particular scenario. Even at this point, you can observe that there is a small little current which is observed over here. Can you see this? Where I am heading? This small gap is there. This small gap. Can you see this carefully? I equal to 0. Below to I equal to 0. There is a small little portion which is there, and that is called as the leakage current. This is called as the leakage current. You can see here. I'm repeating it once again. This is the output characteristics in which I equal to 0 milliamps is a significant role. Why? Because at I equal to 0 milliamps, you can expect that if there is no source, then how come this current is coming over here? We'll discuss that in next class, but for the time being, we'll see that this is called as a leakage current. That will be there for the transistor. Alright, and also another second part is that you can observe that there are three specific regions that we are defining, and that is called as the active region, one is called as the cutoff region, and the other one is called as the saturation region. Active region is a region in which you can observe that the IE value is 6 milliamps. Your IC value is almost the same. So it is a region where the collector current is almost equivalent to the emitter current. It's basically a kind of stationary current. It's a constant current that is going through. On the other hand, if you take the saturation region, you can observe that that is a portion where IC current is actually reducing drastically. You can observe over here. When VCB is negative, this part, VCB negative, this is 0, this is -1, so negative. Collector to base is forward biased, and hence IC decreases rapidly. So that is why we are getting this particular graph. Okay, so this graph is called as, this portion of it, this blue color part is called as the saturation region, and the portion where this leakage current is expected, this is called as the cutoff region. So these are the different parameters and the key points or highlights from the output characteristics which we can observe. Alright, so let us stop at this point. We will discuss about the CE because it will be same as that of the previous, and in fact we will discuss this even in our labs. So hopefully the things will be little easier even in discussing in lab as well. Alright, so let us wind up the session for today. I will as I said, so I'll stop recording first. As I said, I will